We are going to discuss first. We will solve the problems on the means last time derivation, that is derivation of boundary layer, and then we will solve some problems, and then we will talk about the new problems. Okay, so okay, so like last time we discussed the method of solving of a Blasis solution. So uh, now we are going to discuss about the forces on submerged bodies, and this is slightly different. Like in the earlier part, what we said that forces on submerged, like on static submerged body. Now we are seeing in a forces where the body is moving. So suppose there can be some condition like you have a body, okay, and there is stagnant air, and this is moving. Like the body is, there can be two conditions or three conditions. In first condition, there can be possibility of the body is moving, but the air is stagnant. Like you can say the aeroplane or yes. Now second thing is you have a moving air and the body is stagnant. Then so you have a moving air and a body is stagnant. Third thing is you have a what you say moving air and a moving body. So suppose it can be like both is moving in the same direction or opposite directions. So these two cases are nearby similar, and this case you need to use the relative velocity method. You need to use the relative velocity method. Now, so why we are studying this? So last time we discussed more about so sub last time we discussed about the drag and the lift. So that is means you can say that okay, like drag and lift are two major forces occurs in moving submerged bodies. So whether the drag or the lift will generate and how they generate, what is the why they are generated, we will study this. So suppose this is your body and a flow is happening in this direction. Okay, some air is flowing in this direction. So suppose this is air, which is flowing with u naught. Okay, so if you see, you will have two forces. One force will be in perpendicular to the direction. One be, oh sorry, one will be in perpendicular to this flow field. One is parallel to this flow field. This perpendicular force is called a lift force, and the parallel force to the flow field is drag force. So drag force is parallel to the flow field, and the lift force is perpendicular to the flow field. Now, as you know that this will result in some resultant force Fr if you apply a vector addition rule. Now, drag force, our objective should be like we want to minimize drag force as small as possible, and lift force should be as large as possible. Why? Because lift force, like in the designing of an aeroplane, or means you have any body over which flow is happening, the drag force will reduce the momentum because of its surface. And the lift force is important because, like, if you have an aeroplane, you want to produce a lift so that it can take off. So it will this FL. So now, if I just suppose this is your body, and here this is your aeroplane, suppose, and the or any, and this is your thrust. So if you apply, this is your lift, this is your weight. So if you apply the force balance equation, you can say that lift is equal to weight, that is mg, and drag, thrust minus drag, is equal to net force, that is equal to mass into acceleration. So that's why I want to reduce the drag so that we can we can get like what you say, a net acceleration term. So how this drag comes from where this drag comes from, and how this lift force is originated. So you understand the definition of the drag and delay. So drag is defined as the component of the total force in the direction of motion. Okay. Lift is a component of total force in the direction perpendicular to the motion. Now we will try to derive the expression. So suppose this is an arbitrary body and the flow is happening in this direction. Now suppose at this point, this is your x point, and here this is your what you say, take elemental area dA, and now the normal of this elemental area is in this direction. This is your normal. Now take this theta. This is your theta angle. So if this is your normal, this is your like perpendicular to the normal or parallel to this surface, and this is your 90 minus theta. So if this is 90 and this is all, this is theta, if this is theta, this is your perpendicular, means this is your 90, and total is 180. So if you can subtract, you will get this angle as 90 minus theta. Now, as you know, this is the pressure force. Perpendicular to the surface is the pressure force. Parallel to the surface is the shear force. Now, if we apply, so I said that drag force is parallel to flow field. Parallel to flow field, and lift force is perpendicular. Now, what is let's suppose this is moving with unit velocity. So, what is dF for this elemental strip? What is the drag force? So, parallel to flow field, if resolved in the x-axis direction, you will get PdA cos theta plus tau dA cos 90 minus theta. Or otherwise, it is, this is in whole, uh, P dA cos theta plus integral of tau sin theta dA. So this is your in on the elemental strip. What is the drag force in x-axis direction? So total drag force is equal to integral of P dA. Oh, sorry. We should not put integral because it's elemental force. Okay. Now total is P dA cos theta plus integral of tau sin theta dA. This is your expression for the drag force. Now what will happen for the lift force? So we can copy all this. Now we will try to find the expression of drag or lift force. So lift force is what we say is a perpendicular to the system. So what is perpendicular to the flow field? So for any arbitrary surface, if we take elemental area and take the in the perpendicular direction, so it is dfl is equal to p dA sine theta plus tau dA sine 90 minus theta. Now just if you rearrange, it will be p dA sine theta plus tau dA cos theta. And if you take the total summation of along the whole surface, you will get p dA sine theta plus tau dA cos theta over the whole integration over this dA. Now you can say that, okay, your lift force also correspond to the pressure force and the shear force, and your drag force also correspond to the pressure force and shear force. Therefore, we can say that drag force has two components, pressure drag and shear drag. So we can say that drag force has two components. One is pressure drag and the second is shear drag. And then lift force has two components, that is pressure lift and shear lift. So we can say that in this way you can get what is like uh, two different parts of this. Then you have a coefficient of drag. Coefficient of drag is defined as drag force, or I should write in the earlier slide. Coefficient of drag is defined as what is called the drag force divided by the available pressure force. So you can say it is half rho u square a. So this is none other than inertia force. Okay. So inertia force is the characteristics of pressure difference. Characteristic of pressure difference. Now this is the coefficient of drag force. So if you know the coefficient of drag force, you can multiply with the inertia force to get the total drag force. Now one is called the coefficient of lift force. Coefficient of lift force is defined as FL by half rho u square A. Okay. And what is this A? This A is the projected area. This is not a total area. This is a projected area. So suppose if this is your body and the flow is happening, so for drag force, the projected area is what you will get on this. This is your projected area, and the lift force is what you will get at this surface. This is and this is also called the projected area. Okay, now you can understand that we have different types of forces. One is what is called a pressure drag, one is called the shear drag, and now we will try to solve one or two problems so that we can understand what is the meaning of each term. The question is a flat plate of 1.5 cross 1.5 meter moves at 50 kilometer per hour with in air of density, you can say, take 1.5 kg per meter cube. It is given that the coefficient of drag and coefficient of lift are 0.15 and 0.75 respectively. You need to find what is the lift force, drag force, and total resultant force. Okay. Now, suppose this is your plate and the flow is happening in this direction. So it is given that, so first, what is the velocity of the air? It is 50 kilometer per hour. So if you multiply and convert in meter per second, okay, so it is 13.8 meter per second. The area of the plate is 1.5 into 1.5, that is 2.25 meters square. And it is given that density is equal to 1.15 kg per meter cube. Now the lift force is CL into A into half rho U square. So the CL value is given 0.75 into area is 2.25 into half into rho is 1.15 into U square, it is 13.8. Yes, U square 13.8. So if you solve this, you will get 187.20 Newton. And the drag force is CD into half rho U square into A. And if you just put every value, you will get a CD of 37.44 Newton. And the resultant force is FL square plus FD square under root, that is FR, is equal to 190.85 Newton. So in this way, you can like solve get how to get the values, and then we have another question. It says a man weighing 90 kilogram force. Kilogram force means kilogram into, you can need to multiply F. It is, you can say it is a mass, and this is what is you multiply with the gravity to get what is the total weight. Descends to the ground from aeroplane with the help of parachute. And it says that because of the parachute, it is resistance to the air, so it is moving down with a uniform velocity of moving down with a uniform velocity of 20 meter per second. Given coefficient of drag is 0.5, density of air is 1.25 kg per meter cube. You need to find what is the diameter of the parachute. So it is, suppose it is like this. We have a parachute and a man is, so suppose this is your man and he is connected to this parachute. Now this is the weight of the man, 90 into 9.281 Newton. You will exert because of the air, a drag force will be exerted in the top direction, and it is going down with a 20 meter per second. So therefore air will went up in the 20 meter per second. Now, uh, what is this FD drag force? It is CD into area into half rho U square. CD is given 0.5. Area is, what is the projected area over which this is happening? So if you say it is pi by 4 d square, pi by 4 d square. This is a total area of this parachute. So if you take this and you will draw a circle because parachute look like a circle. It is pi by 4 d square into half 1.25 into 20 square. That and the drag force is equal to what is the weight of the person because it is moving with a uniform velocity. Therefore, drag Fd is equal to weight of the person because it is moving with uniform velocity. Now, if you solve this, you will get this is right hand side is and left hand side. If you put every value, you will get like 20 square and everything. So it is 0.5 into pi into 1.25 to 20 into 20, and this 4 and 2 will go here 8. So into d square. So if you solve d square, it is 8.9946, and d is equal to under root of this. You will get 2.9 meter, approximately equal to 3 meter. So this should be the diameter of the parachute so that it moves with a uniform velocity 20 meter per second, carrying the weight of this person. Okay. Now similar problem can be arise like suppose in a similar problem it is given similar problem you can be asked about the diameter is given, weight is given. You may ask what is the velocity over which it descends. The similar problem you just need just to put the velocity v square and you will get what is the velocity over which it came down. And in the third problem, it can be asked that your velocity is given, your diameter is given, then how much weight, what is the weight of the person for which this velocity can be achieved. So in similar fashion can be done. Another question is, it is given that you have a kite, okay, and a string is attached. The direction of the string is wrong. It is in this direction, and the air is blowing in there. So here we are producing, here we are giving a 22.5 kg force. Now, this is your theta 1 and this is your theta 2. So theta 1 that is with the horizontal, it makes is 12 degree and here theta 2 is equal to 45 degree. And what it says is the wind is blowing at a speed of u is equal to 30 kilometer per hour. So if you put 30 into 5 by 18, so the velocity is 8.3 meter per second. Now you need to find what is drag, what is lift. So you know that this is the total force that is exerted, and this force has two components. One is this component, one is this component. This component produces a drag, this component produces a lift. Okay. So if I say this 2.5, so I should say this is your like component of 2 point, this will produce the drag and this will produce the lift. So the formula we say derived is Fd is equal to, because of the pressure difference, we have a drag. So 2.5 into what to say cos 42. So it is cos 45. So in this direction, so it is 17.34 Newton, and the lift force is sorry, this is 2.5 into 9.81 because it is in kgf into what you say is perpendicular to the wave, and that is sine 45 degree. And also the kite has a weight, and the weight of the kite is zero point 0.4 kgf. So weight is zero point 0.4 kgf. So will get a zero point 0.4 into 9.81, and the total force, that lift force you will get is 21.26 Newton. This is the lift force. So lift force and this is drag force, this is in the vertical direction and this is in the horizontal direction. Now you can be asked what is the coefficient of drag? So force of drag divided by half rho u square A. Okay. So if you just the drag force and if you just put the drag force is 17.34 and divide by half rho is 1.25 into u is 8.3 whole square into the area. So we will get a drag force of 0.624, and similarly coefficient of drag is 0.765. Now we will see about the pressure drag and friction drag. So little bit more. So pressure drag and shear drag is also called as a friction drag. So you know the expression is Fd is equal to integral of P cos theta dA plus integral of tau sin theta dA. Now so therefore what it depends. So therefore Fd depends on you three things. One is theta, second is area, and the third is fluid. Okay. So on which what like you can simply say what is the shape of the body, what is the position of the body, and what on which the fluid is flowing. So suppose when you so okay, this is like the force on drag depends on. Now suppose we have a body and it is lying flat like this, and it is placed in a flow field. So therefore the shear stress will act in this way. And what about the pressure drag? So the pressure drag is very small compared to the shear drag. So if you say and what is you say this is a flow field, so theta is like the direction. So for this this is your theta, and this is the flow field. So the pressure is happening in this direction, so it is 90. So pressure difference is not existed at this surface. Only for this small thickness the pressure difference will exist. Therefore, the total pressure drag will only have a component of tau sin theta dA, and sin theta it is tends to 1. Therefore, it is tau uh, tau dA. Now, in this way, what you say that so here the total drag is equal to, therefore total drag is mainly occur due to friction drag or shear drag. and we don't have a pressure drag or pressure difference that will create the drag. Now the second condition is what happens if we put the plate in this way and the flow in this flow field. So you will get what is called as a separation, and it will go like this, and here you have a like wake formation. Okay, so this is your plate and this is your upstream, and downstream you have a wake formation. Now here what happens, so this is your elemental, this is suppose this is your area. Here, if I say FD is equal to integral of P cos theta dA plus tau sin theta dA. Now this is a flow field, this is your elemental area, so theta is equal to 180 degree. Therefore, you will get a pressure drag cos theta or cos theta 180 is equal to minus 1, so you will get minus P cos minus P dA, but this term will vanish. And this is your drag force. Therefore, this in this section, the drag force is mainly due to what is called as a pressure drag, and it exists because you have a pressure difference. Here you have a upstream pressure, here you have a wake formation, and that will exert the pressure. Now, what happens, because this is purely horizontal and this is purely vertical. So what happens is if you place at an angle at any angle theta, there exists FD for which pressure drag and friction drag both exist. Okay. Now therefore the two terms came. What happens if you have a large pressure drag and what happens if you have a large shear drag and small. So suppose you have a body like you have a body and it is placed in a flow field and the flow glides over this surface and there is no any separation takes place or a wave formation takes place. So you can see that the flow is happening in this way and in this way and the separation doesn't take place. Now for this body, if you want to write what is the pressure drag and what is shear drag, so here we have a perfectly streamlined body, therefore the pressure drag minimizes and therefore the total drag only consists of shear drag. And in this region, therefore, in this region, the what is say the wake formation doesn't take place in any of the zone, and the pressure drag doesn't exist much in the contribution to the shear drag. And for this type of body, uh, and for such configuration, these bodies are called streamlined body. Streamlined body. Okay. Such these type of bodies are called streamlined bodies, over which you can say that okay, the pressure drag doesn't exist, no separation takes place, and only the total drag happens because of the friction. And this is possible at low velocities and also at certain position, at certain configuration, certain position, and also with certain design. So if you just increase the angle of attack and make it slightly elevated in this way, you will get separation and you will get pressure drag. Now what this is what is called as streamline body. Streamline body. Now you have a another body that is called as a bluff body. So the second thing is what is called as a bluff body. So a bluff body is defined as is that body whose surface doesn't coincide with the streamlines when placed in a flow. Then the flow is separated from the surface much ahead of the tailing edge as a result of a wake formation. Thus, the drag force will be drag due to pressure difference will be very large compared to the drag due to friction. So, suppose that just like you explained on a plate. So here you have a plate and you just place over it on a surface, like on a flow field. So you have a like you have a wake formation on this surface on the back side, and here you have a flow. So here pressure drag is much larger than friction drag because of separated flow. And therefore, what we say that a very large wake formation happens, and these type of bodies are called what you say a bluff body. Okay. Now you have a streamlined body over which the pressure drag is very small compared to the shear drag, and in a bluff body your pressure drag is very large compared to the. So you can say that here the pressure drag is very small compared to friction drag or shear drag. Okay. Now this is what is the meaning of bluff body and a streamlined body. Now we will so like we will also discuss about what is a like drag force on a sphere. Drag on a sphere. So suppose we have a sphere and the flow is happening. So the CD, the drag coefficient of the sphere looks like something like this, and then it drops, and it is like something like this. Why we are studying the drag on a sphere? Because our rain droplets, cricket ball, and most of the things are placed like in the form of a sphere. So for the sphere, the Reynolds number is defined as rho ud by mu, and if it is very small, your viscous forces are much more important than inertial forces, and therefore what we can say that the drag force that is calculated for this is 3 pi mu d into velocity. This is the drag force that is achieved. Now you know that FD is also equal to half rho square A, or half rho U square into area perforated area of sphere is half, or pi by 4 d square. Therefore, coefficient of drag is equal to into CD. So coefficient of drag is equal to 3 pi mu du divided by half rho U square into pi by 4 d square into CD. The coefficient sorry, and therefore you will get what is called as 24 by rho u d by mu, and this is equal to 24 by Re, and this is what is called as Stokes law. Now in fluid mechanics, there are many of the Stokes law, like many of the Stokes things. One is Stokes law, Stokes law, Stokesan hypothesis. So you need don't confuse with what is the meaning of this. Now for Re greater than 0.2 and less than 5, your CD is given as 24 by Re, 1 plus 3 by 16 Re. Okay. For Re greater than 5 and less than 1000, it is CD is nearly constant and that is equal to 0.4. And for Re greater than 1000 and less than 1 lakh, CD is again nearly constant of 0.5. And for Re greater than 1 lakh, or your CD is equal to 0.2. So for different types of flow, you will get what is called as CD, because I had shown it will decrease from a large value to a small value. So we will solve one question. It is, um, and therefore you can say that the drag velocity in the lower Reynolds number, drag velocity is dependent on the velocity of the system. So suppose in a tank, in a big tank of a fluid, working fluid that is filled, you have a drop, and while you're putting the drop, you have a zero velocity, but because of such a large height, it will start gaining the velocity. And therefore, what happens is, because of inertia or because of inertia, velocity will increase, and because velocity is increasing, drag will also increase. And at some point, your inertia is equal to what is called as drag, and that is called the terminal velocity. After that, it will not increase. And oh, sorry, inertia plus weight. So suppose this is a body, so you will have a weight mg, weight plus buoyancy. So you have a mg, and you have a buoyancy force fb, and you have a top as drag force fd. So you have a weight that is mg plus rho of object minus rho of, so it is, I should write it as minus rho of what is the fluid into volume of the fluid into g. This is a buoyancy force, is equal to the drag force, that is 3 pi mu du. Now we know what is the mass, what is the working fluid, what is the volume of the fluid that is submerged. So if you just shift it right, that is mg is equal to 3 pi mu du plus rho of f into v, volume of the submerged part, into g. And if you solve this, you will get what is called as a velocity. Just a second. Okay. So you will get a velocity, and that velocity uh, will give us the terminal velocity, because the force is balanced. That is the velocity that is not accelerated. So that is called as a terminal velocity. After that, the velocity will not increase or decrease. So this is like what is called as a drag concept, and we can say that like suppose if you solve one question and you are it says that you have a drop metal ball of a size 10 raised to power minus meter in a fluid of specific gravity 0.95, viscosity 15 poise, and density of the metal is given as 12,000 kg per meter cube. You need to find what is the drag force. So drag force is given as 3 pi mu du. But we don't know what is called as the u of the surface. So we need to like find out. So ultimately this drag is equal to the weight of the object plus the like sorry. As you know that this drag plus buoyancy force is equal to weight of the body. Now here weight is given as 12,000, that is density into uh, what is called as the volume, 4 by 3 pi r cube, and the force of drag we need to find, and the buoyancy force is that this is the volume that is displaced the liquid of 0.95 into 1000 into 9.8, and this also multiplied by 9.8. So this is your weight of the body, this is your buoyancy force. If you solve, and this value will come as 0.000493. This value is coming as 0.000039, and the force of drag that it will come as 0.000454 Newton. This is your drag force, and if you just FD in is equal to 6 pi or 3 pi mu du, if you just say, you will get a terminal velocity, and terminal velocity is 0.016 meter per second. Now, after calculating a terminal velocity, check the Reynolds number. What is the Reynolds number you are getting? Rho ud by mu. It is 0.02. If you get Reynolds number greater than 0.02, oh sorry, if you get Reynolds number greater than 0.2, then apply different CD. Different CD. Okay. So now we will take like 5 minutes break, and then we will start the next part of this what is called as next portion of this. Okay, so we will take 10 minutes break. So now we will start on what is called as the integral solution of a boundary layer. The last two earlier lectures we had discussed on the order of magnitude analysis and Glasses solution. So now we will start integral integral methods of solving boundary layer. Okay, so just a second. So in integral method, what happens is, like we had discussed about the Glasses solution and order of magnitude analysis, but you know, Glasses solution is that is for a very simple shape of a flow over a flat plate. But if you go over a complex geometry, it's very difficult to solve Glasses solution. Then the another method that is known is what is called as integral. So what we do is, suppose we are talking about a general case of a flow over a flat plate, and the flow is happening, and this is your boundary layer. So as x increases, your Reynolds number will increase, and you will have a class of, like, suppose this is your laminar, and then this is your transition region, and this is your turbulent. Now, how we solve the integral method? So let's start with that. Suppose this is a flow that is happening, and so suppose this is the point A. We are taking an elemental strip, what is called as A, B, C, and D. Now this is flowing with u naught velocity, and this is your boundary layer. So you know what is the meaning of boundary layer? Boundary layer means it is a locus of points where the velocity is approximately equal to free stream velocity. Now in the control volume A, B, C, D, so what is the mass that is coming from AD? So if you say, suppose this is your delta X element, and perpendicular to the depth you have a unit distance. So perpendicular you have a unit. What is the mass AD that is coming? So it is rho u dy 0 to delta. Okay, so if you say you have a delta thickness here, you integrate, this is your, like, suppose perpendicular to the length is your unity, perpendicular direction to the flow, you have a rho u dy, this is the mass integrated over along the length. Now what is the mass BC? It is mass of AD plus del x of mass of AD into delta x. So if you increase for the length delta x, this is the increased mass. So if I say it is 0 to delta rho u dy plus del x of rho u dy again delta x. Now you know that mass of AD and mass of BC, applying the conservation law in this ABCD, applying mass conservation, or applying continuity in ABCD. So you can say that whatever mass is coming should go out. Now the mass that is coming is at steady state because no accumulation of mass is happening. So mass that is coming is mass of AD, and you have a mass that is going out is BC. But you can see that there is another term that you can say is the extra mass that is going out. Therefore, there should be some mass that is again entering from other sides. So after all, this is a ball, so no mass can be entered from this side. Only possible where the mass can enter is this place. Therefore, you have what is called as so mass is coming and going. So if I just put and therefore applying the conservation equation, you will get mass of DC is equal to mass of BC minus mass of AD. Therefore, it is del x of it is integral of 0 to delta. Integral of 0 to delta rho u dy into delta x. This is the mass that is coming from the DC. So if I had taken a control volume ABCD, so we had just taken what is the mass that is coming from ED, and then we had taken an elemental strip of delta x distance, and then we had said what is the mass that is BC. That is AD plus delta X of mass of AD in delta x. Now applying continuity in ABCD, you can say that whatever mass is coming is should go out. There should be no accumulation of mass. Therefore, you can say that the mass that is coming in AD and BC, we have a difference that is this element. Therefore, this should be come from the DC so that the mass continuity can be satisfied. Now, this is the mass that we obtained. Now we will apply force balance or force balance in ABCD. So last time we had taken, we will just take this. Now we know that mass of AD is equal to, and also mass of AB is equal to 0, no penetration. It is 0 to delta rho u dy. Mass of BC is equal to 0 to delta rho u dy plus delta X of 0 to delta rho u dy delta x. Therefore, the also we write mass of BC is equal to delta X of 0 to delta rho u dy delta x, and mass of AB is equal to 0. Now applying the momentum conservation, what is the momentum that is coming? So we will write from here. What is the momentum that is coming from AD? Momentum that is in. You know that is mass into velocity. So mass of AD into velocity, that is u. And if you say it will be 0 to delta rho u square dy. We only multiply with u, what you called as, so that you can get the momentum that is coming from it. Now, what is the out momentum from BC? It is mass of BC into u. So it is none other than 0 to delta rho u square dy plus del x of 0 to delta rho u square dy delta x. Now, what is the momentum that will in from DC? Like, what is the momentum that will come from DC? So you know, above boundary layer, you have a u naught velocity. So whatever mass that will come with u naught velocity. Therefore, this is equal to del x of 0 to delta rho u into capital U0 dy delta x. So this is the mass that was there from calculated here, and it should come with u naught velocity. Now, what is the Now, in the last part, we say that there is no any mass that will come from this side, AB, because it's impenetrable. But you will have a shear force because of the fluid motion, and that will lead to the change in momentum. So, or we will do that in the later part. So, if we apply the conservation, if we apply what is called RTT in this equation, you will get what is called as sigma of force is equal to momentum out minus momentum in. So it is not mass, it is momentum. I should write it. Momentum out minus momentum in. Now, what is the summation of forces? So if you see you have a drag force in this backward direction tau, so we will say tau into delta x, because we know perpendicular to the depth we are taking as a unity. This is the force and it should be in negative direction because the flow is happening in the back side. What is the momentum out? It is this term. So I will take a copy of this. Sorry. So this is the momentum that is going out minus what is the momentum that is coming in. So if you say coming in is this and this, so is minus 0 to delta rho u square dy minus del x of 0 to delta rho u capital U0 dy delta x. Now this term will go away and delta x if you take common, you will get 0 to delta rho u square minus rho u capital U dy into delta x is equal to minus tau into delta x. This delta x will go to 0 because this is applicable for all the control volumes. And if you say tau wall, it is delta x of 0 to delta. And we can take common, suppose rho u square, u0 square. If you take this thing common, you will get here as u square by u0 square minus u by u0 dy, or tau wall by rho u0 square is equal to del x of 0 to delta u by u0 u by u0 minus 1 dy. Like this is the general expression of integral uh, methods of solving the boundary layers. And this theory can be applicable for any type of flow. So, like if you say this u is a function of y, because if we know the velocity profile, we can directly substitute in this equation, and you can get what is called as we can get any parameters. So if you say okay, so it is u square. Yeah. Okay. Now this is what is called as the um, this is equation is called as von Karman integral momentum integral solutions integral equation. Now this equation can be applicable to laminar, then transition regions, and then turbulent The only condition is you need to know the velocity profile. Okay. What is the velocity profile for a particular region? So suppose for the laminar, if you know from a general expression, we know it is parabolic profile. For a turbulent, this equation holds the power law. Now we will try to solve some questions so that we can understand what is the meaning of each other term and how to solve this. Now this is like one equation, and last class we had discussed about the momentum thickness and the displacement thickness. So displacement thickness, last time we discussed, it is denoted as delta 1, or we say is delta, and it is equal to 0 to delta 1 minus small u by capital U dy. This equation can be solved if you know the velocity profile and you have a momentum thickness. Suppose I am saying as the delta 2, it is 0 to delta small u by capital U 1 minus small u by capital U dy. Okay, this like all these things we will try to solve. First, we need to know what is the what is the boundary conditions on the, like suppose you have a flow that is happening. What is the boundary conditions? Because if you want to know what is the velocity profile, you need to know what is the boundary conditions. So boundary conditions first, you know that is a no slip boundary condition at this point A. So at point A, you have a no slip boundary condition that is u is equal to 0. Okay, at this point we have a no slip boundary condition. Second thing is at y tends to delta, or at point A, it is y is equal to 0, you have u is equal to 0. At y tends to delta, you have u tends to u naught. This is what the boundary layer, because here we assume that the velocity is the free stream velocity. Third thing is at y tends to delta, your du by dy is equal to 0. Why this is equal to 0? Because here you have a delta and sorry, here you have u naught, and just above it is also the free stream velocity u naught. Therefore, the change in velocity in y direction is equal to 0. Therefore, it is du by dy is equal to 0. We have three boundary conditions. So suppose if you have a quadratic equation, suppose if I am saying my boundary profile look like u is equal to a1y, a0 plus a1y plus a2y square. Then we will put three boundary conditions and we can get a0, a1 and a2. But what happens if we have four boundary conditions? If we require four boundary conditions, we need to know one more boundary conditions. And how that can be get is, you know that this is the equation u del u by del x plus v del u by del y is equal to mu del 2 u by del y square. So if we just, this is your like x direction momentum equation for boundary layer, and assume that it's for the flat plate, we will limit as y tends to 0, y tends to 0 and y tends to 0. What will happen? As u is equal to 0 at y tends to 0, this term will go away. This is also equal to y at v we don't have any penetration, so this is also equal to 0. But therefore, del 2 u by del y square at y tends to 0 is also equal to 0. This is your like fourth boundary condition. Del 2 u by del y square at y tends to 0 is also equal to 0. This is your fourth boundary condition. Now, knowing all this, we will try to solve some questions so that we can get an idea how to solve what is called as boundary layers. So suppose first question we will solve. If it is given, you have the velocity profile as u by u0 is equal to 2 times y by delta minus y by delta whole square. This is a quadratic boundary layer profile. So you need to find what is the shear stress, what is the delta, and like many other things. You need to find what is the delta, what is the coefficient of drag, and everything. We'll try to like give conclude like how to solve this. So you know this is the one common integral equation, momentum equation. This is a one common integral equation. So we will put the equation tau by rho u0 square is equal to del of del x of 0 to delta 2 times y by delta minus y by delta whole square 1 minus 2 times y by delta plus y by delta whole square dy. Now if we just so you have two equations, we will try to club these two equations. So if you just open everything, you will get 2 times y by delta minus 4 times y by delta whole square plus 2 times, okay, plus 2 times y by delta whole cube minus y by delta whole square. Just multiplying both the things plus y by delta whole cube minus y by delta raised to the power 4 dy. So you have y by delta, this is y by delta square, this is y by delta cube. So we will try to sum up these things. So 2 times y by delta minus 4 minus 1, that is minus 5 y by delta whole square. This is 2 and this is 1, this is 3. 3 y by delta whole cube minus y by delta raised to the power 4 dy. This is tau by rho u0 square. So we need to now integrate this term. So del del x of, we just integrate this respect to dy. It is y square by delta minus 5 y cube by 3 delta square plus 3 y4 by 4 delta cube minus y5 by 5 delta 4 and like and the limit is 0 to delta. So it will be del del x of so del del x, if you just put the limit, it will be delta minus 5 by 3 delta plus 3 by 4 delta minus delta by 5. And if you just simply say, it will be 2 by 50 del del x of delta. Now left term, it is written as tau wall by rho u0 square. So if you say tau wall for laminar flow is rho du by dy at y is equal to 0. So as you know, u by u naught, it is given as 2 times y by delta minus y by delta square. So du by dy is equal to 2 by delta minus 2 y by delta square. This is du by dy, so it is into multiply with u naught. And if you just say y is equal to 0, you will get as 2u0 by delta. Now therefore putting things left and right, you will see that it is in the left side it will come as tau wall is sorry, this is mu. Okay, so tau wall is mu du by dy. So mu 2 mu 0 by delta into half, so not half, it is rho u0 square. This is left hand side is equal to 2 by 15 delta less of delta. Now we know that this will go away, and we have, like, if I say 2 will come, like, go away, so it is 15 mu by rho u0 is equal to delta into delta less of delta. So this is none other than del x of delta square, and it is half, because it again you differentiate it with 2 delta will come out and 2 will cancel. This is the same thing. Now if you integrate in the right hand side, 15 u by rho u0 into dx del x is equal to, or 15 by, okay, so it is, yeah, 15 by 2, or it is 30. I think it will be 30. It is 30. That is equal to del of delta square. Now, this is a function of x only, so we will try to integrate this. So it is delta square is equal to uh, 30 mu by rho u0 into x plus some constant. And the constant says, so it is at x tends to 0, delta tends to 0. Therefore, delta square is equal to 30 mu x by rho u0. And if you just do the recalculation, you will get as delta by x is equal to 5.48 upon under root of Rex. So in the Laplace solution, we get as delta by x is equal to 4.91 by under root of Rex. And here this is from Laplace, and this is from von Karman momentum integral equation. Now you can see that it is fairly accurate with the coefficient is slightly deviated. So that will be easy for you to solve, like how to solve this equation. Like this is the delta. Now we also want to find out what the shear stress. So here we have derived the shear stress as 2u0 by delta. So shear stress is derived as 2u0 by delta. And delta we had came across as 5.48 by Rex. 2u0 by 5.48 h into under root of Rex. Now if you just rearrange and solve it, you will get 3.365 mu u0 by x under root of Rex. Now coefficient of drag is equal to Fd upon half rho u square a u0 square. And if you put everything, okay, so this is at any x. So first we need to find what is the total f. Total f is equal to integral of 0 to L tau x into del. So perpendicular to the length is unit, it is tau x into dx. So if you just simply put everything and solve, you will get an equation that will look like this. Like if you put this equation and integrate it here, you will get 0.73 mu u0 under root of rho ul by mu u0 L by mu. So now CD is equal to f, this f 0.73 into mu u0 under root of rho u0 L by mu divided by half rho u square a, and area we know only delta x. So similarly, if you solve or L, if you solve it, you will get as 1.46 divided by under root of REL. So simply by knowing the velocity profile, you can get what is called as the expression for delta. Then you can get the expression for shear stress. Then you can get the expression for the drag. Also for the displacement thickness and the momentum thickness, we can get the expression. So displacement thickness is this much. So if we just take the copy the term, or we can copy the whole term. So for this profile, for this velocity profile, u is equal to u by u0 is equal to 2 by y by delta minus y by delta whole square. If you simply substitute in the delta 1, that is in displacement thickness, you will get 1 minus 2 y by delta plus y by delta whole square into dy, and you will get delta minus this will be delta square by 2, and it is delta again plus 1 by 3 delta. Okay, so this is the expression, and if you just simply solve it is delta by 3. Now what is the momentum thickness? We need to just do the thing to y by delta minus y by delta whole square, and it will be multiplied by 1 minus 2 y by delta plus y by delta whole square dy, and you can simply like rearrange and solve. So it is, I think this is the same expression. Okay, so just a second. Yes, this is the same expression. So you will get 2 by 15 delta. So for this you will get 2 by 15 delta. So this is nearly 0.33 times delta, and this is 0.1 0.126. Yeah, so 2 divided by 15, it is okay. So it is 0.1133 delta. So therefore, you can say that displacement thickness is greater than momentum thickness. This is the conclusion that you can derive from here. Now this solution has been derived for like one velocity profile. There are numerous velocity profiles. Like suppose you have any other velocity profile, as you can see. Suppose you have a unique velocity profile, that is u by u is equal to sine times pi by 2 y by delta. Okay, suppose this is the velocity profile and it is in the sinusoidal form. Now, what will be the what will be the different parameters? Similarly, same thing you need to do. So first we will do with the equation that is tau by rho u0 square is equal to del del x of 0 to delta small u by capital U, 1 minus small u by capital U dy into, okay, so if I just put, it is sine pi by 2 y by delta, and it is 1 minus sine pi by 2 y by delta, and this will be in dy. Now you need to integrate the equation, so we will do slight integrations. First arrangement, sine pi by 2 y by delta minus 0 to delta sine square pi by 2 y by delta dy. So this is also dy and this is also dy. Now this is a simple integration. The first side, it will be minus cosine pi by 2 y by delta, and here you will get pi by 2 delta, and the limit is 0 to delta. Here you need to make it a like what you say a cos 2 cos 2 times theta. So you will get, if you just integrate it, cos 2 times, you will make the 1 minus sine 2 theta, and you just solve it, you will get pi y by 2 delta 1 by 2 by pi by 2 delta minus sine 2 times pi by 2 y by delta by 4 pi by 2 delta. So like this is 0 to delta. If and you solve it, you will get a expression like this in this way. Del del x of 4 minus pi by 2 pi, and it is tau by rho u square into delta. This is the expression, and then the left hand side again will go. So if you say tau wall, so tau wall is mu du by dy at y equal to 0. And if you just put the expression, you will get u pi by 2 delta. So you can simply put both the terms, and you will get, sorry, mu u pi by 2 delta. So it is 4 minus pi by 2 pi rho u square d delta by del x is equal to mu u pi by 2 delta. And if you solve everything, you will get delta square by 2 as delta square by 2 as 11.5 mu by rho u x plus c. And as you know, at x tends to 0, delta tends to 0. Therefore, delta is coming as 4.795 x upon under root of rex. This is also quite similar to like the last time we had did. Last time it was if you say delta is 5.48, here it is 4.795. And then again you can solve for the tau wall and the force of drag. So I will write tau wall is equal to 0.327 mu u by x under root of rex, and force of drag is equal to, or force of drag is not main criteria. If main criteria is coefficient of drag 1.31 by under root of REL. Now what we will do is we will like similarly momentum thickness and displacement thickness can be find out. So for various velocity profiles, the solutions is obtained for delta and CD, the important two terms. So we will look into the expression, and the solution methods can be similar. Velocity distribution, and this is your delta and this is your CD. So first what we solve is the Blasius. So what is the Blasius solution? For delta, it is 4.91 x upon under root of Rex, and the CD is 1.328 upon under root of REL. We only want to look at how close the value is. So if you say this is the Blasius, this is the exact solution that we obtained. Now, what happens if the velocity profile will look like this? Like we had solved in this class. What is the velocity profile if it looks like this? It is x upon under root of Rex, and here it is 1.46 upon under root of Rex. Now we had just solved about the sine pi by 2 u by u0 is equal to sin pi by 2 y by delta, and it is 4.79 x upon under root of Rex, and the CD is 1.31 upon under root of REL. Actually, this is REL. Now you can have different velocity profiles. So I'm writing the final results. It is 3 by 2 y by delta minus half y by delta whole cube. For this, it is 4.64 x upon under root of Rex, and 1.92 upon under root of Ren, and it is u by u0 is equal to 2 y by delta minus 2 y by delta whole cube plus y by delta whole raised to the power 4. It is 5.84 x upon under root of Rex, and it is 1.36 upon under root of Rel. So for different types of solutions, you can get different values, but only the coefficients are changing. And Going with the Blasi solution is difficult because it is more of a iterative method, but you can see that all solutions are nearby similar to the Blasi solution. So similar, if you see like for this velocity profile of a like a quadratic velocity profile, then this sinusoidal velocity profile, then this cubic velocity profile, then fourth order velocity profile, you will get the expressions that are similar. Same. So therefore, if we know the exactly any velocity profile, we can directly get what is called as what is the delta, what is the CD, and also the momentum thickness and the displacement thickness. What is the momentum thickness for that profile, and what is the displacement thickness for that profile. Now, like after 10 minutes, we'll solve to some of the problems. So, like till then, we'll hold a break. Okay. After 10 minutes, we will see. Now we will try to solve some question. Uh, so what we discussed is the velocity profile. So the question is, suppose for the velocity profile u by u is equal to 3 by 2 y by delta minus half y by delta whole cube. So this profile we had already solved, 3 by 2 y by delta minus y by delta whole cube. This is the already profile solved, like solved. Now it says that find thickness of boundary layer at the distance of 1.5 meter from leading edge. Now it says that like suppose this is your leading edge. From here 1.5 meter you find what is the delta. So for this velocity profile we had known that what is delta, that is 4.64 x upon under root of rex, and the fluid that is flowing is with a the velocity is given as 0.2 meter per second. Kinematic viscosity is 0.01 force, and this is water, so rho is 1000 kg per meter cube. So this is the plate. So if I solve delta is equal to 4.64 into 1.5 divided by under root of rho that is 1000. So 1000 into v is 0.2 into x is 1.5 divided by mu that is 0.01 into 10 raised to the power minus 1. So just if you solve, you will get around 12.7 mm. This is the delta at the distance of 1.5 meter from the edge. Now we need to find what is the shear stress. So shear stress is at this location is 0.323 mean u0 by x under root of rex. So 0.323 into what is the viscosity, that is 0.001 into 0.2 divided by x 1.5 under root of rex. So it is 3 lakhs. Okay. So if I solve, just wait a second. It is 0.323 into 0.001 into 0.2 into root of 3 lakhs divided by 1.5. You will get 0.0235 Newton per meter square. Discuss your stress. Now, what should be the drag? Now, this is the shear stress at this particular location, and we need to find what is the drag over the whole length of the plate. So, the plate dimension, total plate dimension is 2 meter long and 1.4 meter wide. So, what is the total drag? So, for the total drag, the formula is 0.646 mu u. All these formulas are calculated from the velocity profile. So we already know what is the value, but again, if we don't know, it will take a long time to solve all these things, and the final expression then only can be solved. So it is 0.646 into 0.001 into u is 0.2 into 1000 0.2 into length is 2.0 divided by 0.001 into 1.4. So the drag is 0.1138 Newton. This is the total drag force. Okay, now we know what is the thickness, what is the tau, at what is the shear stress at a certain location, and what is the drag force. Now, the importance of all this calculation last time also I told you, we can obtain what is the power consumed or what is the power required to supply the air. So power consumed is equal to FD into velocity. So what is the air which velocity? Air is flowing with this velocity, 0.2. So if you just multiply it, you will get 0.2276 watts. So that much is the velocity that will be given. Now, there, if you just now again a different question. So it says air is flowing on a smooth plate with a velocity of 10 meter per second. The length of the plate is 1.2 meter and width is equal to 0.8 meter. And the critical Reynolds number at the boundary layer, like this is the critical Reynolds number. After this region, the turbulence starts. So this is the region where from the laminar region, the transition region starts. So it says that what is the maximum thickness of laminar boundary layer? Maximum thickness of laminar boundary layer with the velocity profile u by u0 is equal to 2 times y by delta minus y by delta. So like if you see this as part, so here this is quadratic. So for the quadratic velocity profile, the thickness is 5.48 x upon RES. So delta is 5.48 x upon under root of RES. But we don't know in the length of 1.2 meter where this particular round number will exist. So we will like if you say it is rho v x by mu, so we need to solve what is the x. We don't know what is x. So kinematic viscosity of air is 0.15 Stokes. We don't know what is the value of x for which this Reynolds number will occur. So what we will do is we will first find what is x. So x is equal to Ra into mu by velocity. Okay, so we will solve Rex is equal to Re into mu by v. So and we know the velocity is 10 meter per second, so we'll get x that is equal to 0.30 meter or is equal to 300 mm. Now we know that after this boundary, after this thickness, what happens is it will change to the turbulent region. So delta is equal to, we need to find at this location that is 0.3. What is the Reynolds number? Reynolds number is already, 2 into 10 raised to the power 5. If you simply put the equation, just a second. If you simply put the equation, you will get as delta is equal to 3.67 mm. So here the in the question the twist is we need to find what is that location where this Reynolds number will occur, and after that what is the delta at this particular Reynolds number. So we need to find what is first x, then we need to find what is the delta. Now we will do one thing. We will try to solve like Like we had solved only for the laminar case, and but we haven't solved it for the turbulent. So we will try to um, in the derivation of one Kalman integral momentum equation, we haven't said that it is for the laminar or it is for the turbulent. So like for the turbulent boundary layer, the u by u0 is generally y by delta raised to the power 1 by 7. And then so we need to find out what is the drag, what is the drag, what is delta and everything. And the given with given condition, like in our for the laminar, we had said that tau is equal to mu du by dy at y is equal to 0. But here we will use what is called as tau is equal to 0.2 0.0225 rho u square mu by rho u delta raised to the power 1 by 4. Okay, so just simply applying the von Karman equation, it says del del x of 0 to delta small u by capital U 1 minus small u by capital U dy. Now small u by capital U is delta 0 to delta y by delta raised to the power 1 by 7 1 minus y by delta raised to the power 1 by 7 dy. Now if I just substitute it, it will be 0 to delta y by delta 1 by 7 minus y by delta 2 by 7 dy. So del del x of this equation. So if I integrate this first term, it will be y raised to the power 1 by 7 plus 1 by delta into 1 by 7 plus 1. And you will get as 0 to delta minus similarly y raised to the power 2 by 7 plus 1 by 2 by 7 plus 1 into delta 0 to delta. And if you just solve, you will get del del x of 7 by 8 y 8 by 7 by delta 1 by 7 minus 7 by 9 y raised to the power 9 by 7 by delta 2 by 7, and it is 0 to delta. So if you solve this, you will get as 7 by 72 delta x of delta. This is tau by rho u square, and this term is given as 0.0225 mu by rho u delta 1 by 4 is equal to 7 by 72 d delta by dx. Okay, now you can substitute this term and you will get delta expression. So if I just substitute left hand side and right hand side, you will get delta as 4 by 5. Delta raised to the power 5 by 4 is equal to 0.2314 mu by rho u 1 by 4x plus c. And at x tends to 0, delta tends to 0. Therefore, c tends to 0. Now, the delta will come as 0.37 mu by rho u 1 by 5 x raised to the power 4 by 5. Or it is 0.37x upon rex raised to the power 1 by 5. So like this is what is delta. Similarly, you can find what is tau wall because tau wall is written as rho u square 0.0225 into mu by rho u delta raised to the power 1 by 4. You substitute delta, you will get expression. So I'm writing the expression directly. So tau 1 is 0.0577 rho u square by 2 mu by rho ux 1 by 5, and coefficient of drag that will come as, FD upon half rho u square A, and FD is 0 to L tau wall into area, or sorry, into dx. If you just integrate everything, you will get CD is equal to 0.072 upon REL 1 by 5. So, like for this turbulent region also, you will get what is called as, this is for turbulent velocity profile. For this turbulent velocity profile, you will get what is the delta, what is the formula for delta, and what is the coefficient of drag, what is shear stress at any location x. At any location x, this is the shear stress. Now we will try to look in the some, like this is the all these things are some quantitative things. So now what happens if you have suppose if you have a turbulent and a laminar boundary layer simultaneously. So like I had said that in a flow over a flat plate, if you have it happens that after some time the boundary layer changes from laminar to turbulent. So this is your laminar region and it's a turbulent region. So total drag on laminar and turbulent region. So what is the total drag on laminar and turbulent region? So okay. So for that, what you need to do is uh, so we need to find what is the drag force in the laminar region. So drag force in laminar plus over whole length 0 to L. So suppose this is 0 to L and this is L1. So 0 to L1, what is the laminar region plus force of drag over this whole length 0 to L turbulent in turbulent minus force of drag in this 0 to L1 in turbulent. Like this is the total drag that will be obtained if we have a mixed region, FT total. Like you assume that this much is easy to find. What is the length L1? You will get this. Now why we are saying it is 0 to L, because the integration of all the things has been made from 0 to L. Because CD has been derived from 0 to L. So if we want to apply directly that CD, you need to take that, okay, all from 0 to L, the turbulent region is there. Then we subtract from 0 to L1, and you will get, this is like we had like suppose that this here it is turbulent, but here it is not a turbulent region. So we'll subtract that part and get the total drag. Okay. And what is the critical Reynolds number where the transition happens? The critical Reynolds number is 5 into 10 to the power 5 for a flat plate. So if the flat plate the flow is happening, you need to find what is the x for this critical. And when this x is known for this critical, you divide the region and then say that, okay, 0 to x, this is laminar, plus 0 to complete L turbulent, minus 0 to x again in turbulent. So in this way, the equation will be solved, and we will try to look like how to obtain the drag for this particular mixed region. Okay. So that thing we will solve. So one is the question says you have a water flowing over a thin smooth plate. Water is flowing over the length that is given as 4 meter and width is given as 2 meter. with a velocity of u is equal to 1.0 meter per second. If the critical Reynolds number is 5 into 10 raised to the power 5, the question first, what is the distance from the leading edge where the like what is the distance till laminar exists? Okay, first thing. And dynamic viscosity of water is 9.81 10 raised to the power minus 4 Newton second per meter square. So this x is Re critical is equal to rho Vx by mu, and Re critical is 5 into 10 raised to the power 5. That is equal to rho is 1000, velocity is 1.0 into x is we don't know, and mu is 9.81 into 10 raised to the power minus 4. So you will get a x value of 490 mm or 0.490 meters. So in 4 meters, till here only the laminar exists. Suppose if I say. Now we need to find thickness at that this delta. So delta by x is equal to 4.91 upon r is from the glaciers, or you can use any. It is approximately 3.4 mm delta. This is the boundary layer thickness. Now the next problem is what is the drag, like total drag over the system. So like I said, we need to find the drag in a distributed way. Like, so first, what is the drag on the plate till 0 to 0.49 meter? Because it is a laminar, we know what is the value of CD for laminar, and we multiply with half rho square A. So CD is 1.328 upon under root of REL into half into rho is what you say is 1000 into u square is 1.0 meter per second, I think, yes. Into area of cross section is 4 into 2, 8. So if you simply just, no, actually it is still 0.49. So it is 0.49 into 2. So this is a drag force. And if you solve till this region, you will get 0.92 Newton. Now, what is the drag force from 0 to 4 meter because of turbulence? So we will do as CD. So CD is 0.072 divided by under root of sorry REL raised to the power 1 by 5 into half into 1000 into 1.0 into now the complete length, that is 4 to the 8. And if you solve over this EG length, it is 13.72 Newton. And then you need to find what is the drag from 0 to 0.49 in turbulent. And please solve this. I will be available in 5 minutes. Till then, you solve this part. Okay, so now we will try to solve the second part. Still, now we will try to solve the second part. What is turbulent till this region? So if you solve it is again 0.072 upon r real is power 1 by 5 into half into 1000 into 1.0 into 0.4922. So if you solve this, you will get 2.6 Newton, and therefore the total drag total, you will get this as laminar is 0.92 plus 13.72 minus 2.6. So you will get as and nearly 12.08 Newton. This is the total drag. So like this, in this way, you will try to solve the problems. And we had discussed, like I had discussed most of the numerical problems, like how to solve for different velocity profiles, laminar or turbulent region. Now, what we will do is we will go with some concept of how the separation will take place, like separation of boundary layer and how we can avoid the separation. So, like suppose you have a body like this, a body like this, okay, and this is a very far streamline where the you don't have any effect. Like this is your suppose this is your um, um, region, and this here you have a inviscid region. So this is a far more streamline where no any effect of this boundary is present. Now, if you see, like this wall is even one streamline. So this is size equal to constant one streamline, and this is size equal to constant one streamline. So as we all know, in between the streamlines, in between the streamlines, your mass is held constant. So between psi 1 and psi 2, like this, suppose this is psi 1 and psi 2, your mass is constant. And if it is incompressible, therefore volume is also constant. Now, if you see at this location, suppose some mass is entering M1 and volume is entering V1, so I'm writing it like V in this way because velocity is also V. At this location, the same volume will be there, and at this location also same volume will be there. So volume is constant. Okay, same, everything is same. Now here, if you see in between the streamlines, the passage area of cross section is decreasing. So till here to here, area is decreasing. And since volume is held constant, you can say that the velocity will increase. So in this region, the velocity will increase. Now, here what happens is your area is decreasing, therefore your velocity will decrease. Now, so because your boundary layer is very thin, so whatever be the pressure gradient exists in this region will be superimposed in this region. Therefore, if we apply the, like, what is the Bernoulli equation while changing the velocity from here to here, it will say that dp by dx is equal to rho uc duc by dx. Like from the Bernoulli equation, p plus half rho u square is equal to constant. If you derivate it with respect to x, you will get this term. Now, since velocity is increasing and x is increasing, this term is positive and this is negative because it will go right hand side. So therefore, this term is negative. This term is negative. And in the right hand side, this dp by dx is positive. Why? Because your your velocity is decreasing with respect to x, so it is negative, and negative means positive. Now what happens is in the here it means that here you have a larger pressure gradient, here you have a smaller pressure gradient. Therefore, the flow will happen from this side to this side. Now here it says that here you have a lower pressure gradient, here you have a higher pressure gradient. Now what is the meaning of this? This is the meaning is if you don't have sufficient velocity in this direction, the inertia force, the flow will happen to from the back side. And this is called a separation of flow because now the boundary layer will, like if I draw the velocity profile, the velocity will look like this. But at this point, the velocity will look like this. Now the flow has separated and it has reversal. So that is called the flow separation. The flow has been separated, like so. Let's assume in this way. So here we have a no slip boundary condition, and nearby we have very less velocity. And the pressure gradient says that here you have a higher pressure gradient at this point, and it has a lower pressure gradient. And now the flow will initiate in this direction, and here you will see that okay, your boundary layer goes like this, but here you have a flow reversal, and this is called the reversal, and this is a formation of eddies because here you have a pressure gradient that exists in this direction, and here we have a velocity in this direction. So it will form a vortices, and this is called as a flow separation. Flow separation. And flow separation initiates when this uh, dp by dx is equal to 0. It initiates when this is equal to 0, and like it has a possibility that after reaching this, the flow separation will take place, and you will get like what is called as a pressure drag because of the difference in pressure in between upstream and downstream and upstream. Now this is very it mostly happens like if you have aerofoil shape and you're at a certain angle of attack, and if the flow is happening, you will find that okay, after this region the flow will separate and it will like form a vortices behind the surface. So because of the vortices, there's a large drag because of the pressure drop. Now our aim is how to like what are the things that can prevent the drag. So like first we need to see the velocity profile. First we will conclude this. So suppose this was the thing, and this is the some term. So if you say my boundary layer goes like this, and here you have what is called a separation. Here you have a separation. Now we will draw the velocity profile. So here the velocity profile will look like this because the flow is attached. Here also it is attached, going like this. But here the flow separation takes place. So at this point, sorry, at this point you have a like something like this because here you have what is called as a stagnation point, and after that what you have is you have this flow reversal, and the flow is reversed in this direction and then again meet the what is called as a mean stream velocity. So this is what is called as a flow separation. Okay, now we will try to see the methods of preventing the separation. So methods of preventing what is called as separation. So first thing is, so suppose last time we discussed that okay, um, you have some aerofoil shape and the flow is happening in this direction. So it is seems that here the separation will take place. Um, Here the separation will take place. Now what we will do is we will put some ports here. This is called ports. So this is called ports, and we will produce a suction. Now, what happens with the suction is whatever be the this what is called as a reversal will be sucked out, and the boundary layer then will be attached to the surface like this. This is called as what is called as a method of suction by which we can um, reduce the separation, and this is possible for the slow moving fluid. The and another method is if you there is a flow, you can do one thing. You can make a slit here, and no, not in this direction. You can make a slit here and may merges to this direction. So now, if I say I have this slit, now what happens is because of stagnation point, there is a pressure, higher pressure, and here we have a lower pressure. Now the flow will happen, and the boundary like the uh, wall, there is attached to the wall, and here because of this higher pressure difference, it will push the liquid, and the what you say the boundary there is or we have a no separation thing will happen. Okay. Now the third thing is what you can do is you can induce vortices into the boundary layer. So if you just induce the vortices into the boundary layer, you can avoid the separation to take place. And there are lots of methods by which the separation of the boundary layer can take place. But it is very important to know that why we are doing so much methods to do to avoid the separation. And the thing is, it is important because if the pressure if the separation will takes place, there is a possibility of a large pressure drop. And this large pressure drop leads to the large drag force, because we already see that the drag force consists of this pressure drag plus a shear stress or friction drag. Now, with this with this separation point, we have one thing to cover. The separation will occur when your del u by del y at y is equal to 0 is equal to 0. That is, there is no any what is called as a flow attached to the wall. So if this is occurred, this is the verge of separation or separation point. And if so, I should write here del u by del y at y is equal to 0 is equal to 0 verge of, or I should say point of separation, point of separation. Del u by del y at y is equal to 0 is negative. If it is negative, it is said that flow is separated. And if del u by del y at y is equal to 0 is greater than 0, we say that the flow is not separated or remain attached. Remain attached. So this is the criteria for separation. Criteria for separation. And we will try to look into some of the velocity profiles and how whether they are separated or not. So we have first a velocity profile as u by u0 is equal to 3 by 2 y by delta minus half y by delta whole cube. So first we need to find what is du by dy. If you find du by dy as this, you will get 3 by 2 y square by delta cube. And at y is equal to 0, you will get as 3 by 2 delta. So you can see that since delta is positive, this term is greater than 0. Therefore, the flow is remain attached. Now the second velocity profile is u by u0 is equal to 2 times y by delta whole square minus y by delta whole cube. And we had said that the flow will be separated when this condition will exist, and if the point, and if it is greater than zero, it is remain attached. And if it is equal to zero, it is a point of separation or the verge of separation. So we will find del u by del y at y is equal to zero. You will get 4 times y by delta square minus 3y square by delta cube at y is equal to 0. And you will get as this is equal to 0. Therefore, it is said that this is at the verge of separation. Now, the third profile is, suppose it is u by u is equal to minus 2 y by delta plus y by delta whole square. Du by dy at y is equal to 0 is minus 2 by delta plus 2y by delta square. And if you put y is equal to 0, you will get minus 2, sorry, 1 by u. I had missed 1 by u everything. Minus 2 by delta into u. If I say du by dy at y is equal to 0. Now this is less than 0, therefore the flow is separated and it is not attached to the body. So this in this way you can obtain whether the flow is separated or not, what is the reason, and how to avoid the separation of flows. Like these are the things that will came across to you, and you can help to solve what is the like how the problem. And similarly for all the other all the other profiles, you can get what is called as displacement thickness, what is called as momentum thickness, and and then what is your boundary layer thickness, and everything can be known. Now let me see if any other question is remaining, so that it will be helpful in solving the assignment problem. Okay, so now we have another thing. Just from a curiosity point of view, I will explain to you. You that is called as a cricket ball in swing and outswing. Like this is basically mostly based on what is called as a fluid mechanics. So, like suppose this is your this is your stump, and the bowler is bowling with the same position of. So you have a ball, and you have a same position in this way, in this direction. So if the ball if the bowler is bowling in this direction, it will be called as a in swing. Now that there is a difference between spin bowling and a swing bowling. So if you say the swing bowling, the spin bowling is mostly based on what is called as a Magnus effect. So if the ball is spinning, it is called as a this happens because of this Magnus effect. But the swing bowling is happening because of a different reason. So if you say the ball is there, and this is what is called as a stitching of the ball, and this is a outswing. Now, why this happens? So suppose the air is flowing in this direction. So here you have a sorry, here you have a longer time the boundary layer is attached and then separated. Here what happens is the air will go, and because of the turbulence reason, In the turbulence region, the bonding gets separates early. So here the separation will take place on at this point. So this is the separation point on this side, and this is the separation point on this side. Now, because of the difference in separation point, there is a tendency that there is a force that is exerted in this direction, and this will lead the ball to going in this direction. Like this is your stumps. Now, for this configuration, the similar thing will happen. The flow will happen. Here we have the what is called as a thread, and the thread will separate the what is boundary layer because it will lead to the turbulent region, and in turbulent region, the earlier the separation will take place, then at this point we have a difference that is at the more at a larger curvature the separation will take place, and again this will induce a force in this direction, and it will lead the ball to go outside. And that is the difference between the what is called as a cricket ball, and it happens because of separation. So uh, when we say the spin of cricket ball or a golf ball, not for the golf ball, for the cricket ball happens because of Magnus effect. The is the swing the swing of cricket ball happens because of separation and turbulence. Separation and turbulent flow. Like that is the difference between how the swing will happen and how the spin will happen. And there is another term that is called the seam bowling. And seam bowling means your ball will go in this way at the same position. It hits the ground, and because of the seam, it will deflect in the left and right. So this is from the mechanics side. It is just a mechanics side. Like it will go left or right. It depends on on what seam angle it lands. But swing is mainly happens because of this separation and turbulent flow. Okay, so like in next class to TA class, we will discuss all the things. Like we'll discuss mostly the numericals. So we'll like cover the numericals of all the fluid mechanics because I think the classes has been over from the professor side. So we will. And today we had discussed about the one fundamental equation, the pressure drag and the friction drag, and what you say as separation of boundary layer. What is the criteria for separation? How to prevent the method of the separation? And then we had seen about this basic of the in swing and the out swing ball. So this is like all like what we had discussed, and we will meet in the next class. Till then, try to solve some problems and try to solve the problem and then obtain what the like how to solve this one Karman and everything. Okay. So we will meet in the next class.